Okay, so let's begin. First things first, any questions on the homework? .3.
5.2 and 5.2.
Huh?
We got 5.2 and 5.2.
Okay, questions on 5.2? What does that say?
Integral of cosine x dx.
The
Integral of cosine x dx.
integral of cosine x,
Cotan.
cotangent x dx.
You have to show that it equals to ln sin x, ln of dash.
Okay, how would you do that? Huh? Right, this is just cosine x over sine x, and then the next step would be what? U equals sine x, right? The division by sine x is what makes it complicated, so you try to substitute that out. The derivative would be cosine x dx, which we have here. So this would give us the integral of 1 over u du, which we know gives us ln u plus c, which is ln of sine x plus c. So it's just using your trig identities, rewrite it, do a substitution, and now we know how to integrate that because we know about the log function. Any other questions?
27. To differentiate f of u equals ln of u over 1 plus ln of u.
F of u equals ln of u over
1 plus ln of 2u.
ln of 2u, right, the 2 u's inside the ln. Okay? And we want to differentiate that. Okay, what do we do? We need the quotient rule. Okay, so we need the bottom times the derivative of the top, which is minus the top times the derivative of the bottom, which is right, so derivative of 1 is 0, derivative of this is 1 over 2u times 2, so the 2's cancel, you just get 1 over u. All over the bottom squared. This bottom times derivative of top minus the top times derivative of the bottom over the bottom squared. That is the quotient rule, and right now we're going to see if we can simplify anything. Well, first, 1 over u is a common term. I can just factor that out. So I have 1 plus ln of 2u minus ln of u all over this u can come to the bottom. Can you simplify the top?
Yeah.
How?
ln of 2u gives you ln of 2.
Right,
Plus-
ln of 2u is ln of 2 plus ln of u. So this guy can split into ln of 2u plus ln of u minus ln of u, so the ln of u's cancel, and I'm just left with 1 plus ln 2 over this. So that will be your answer. Other questions?
Actually, 20 minutes. 1 equals ln of 2 minus x minus 5x.
2 minus
X is equal.
minus 5x squared. It's not too value. What are we supposed to do with that? Just differentiate? So How do you differentiate it? Hmm? So it's 1 over this times minus 1 minus 10x. Do the absolute values matter? Why do we need the absolute values?
Because they're in the domain.
Right, but doesn't the absolute values affect this guy? I know that absolute value x, for example, right? That's just equal to x if x is positive, it's minus x if x is negative. Does that actually change the answer here? Do we have to worry about signs? We actually don't. Why do we not? Because assuming the inside is positive, right? What's going to happen? The absolute values won't even matter. So you just do this. But assuming the inside is negative, what would the absolute value do? It's going to take the negative of everything, right? So we're going to put 1 over the negative of this. But once this is negative, what's its derivative going to be? It's also going to be the negative, right? You'll have the negative cancel, right? So this is going to be the answer in either case. Right? But still, whenever you see absolute value, that's something you have to consider, right? There's always the sign change of when this thing switches signs, right? So you have to consider it. But it actually doesn't make a difference here. So it's just minus 1 minus 10x over 2 minus x minus 5x squared. Other questions? 73. We went that far? Okay. What does that say?
What's the definition of a derivative to prove that limit x equals 0 ln of 1 plus x over x equals 1.
So I have to prove this. Okay, so we know the definition of derivative, right? So let's say I have call, say given a differentiable function f of x, we know that the derivative at a point A is defined, how do we define it? By definition. H approaches 0 of f of x plus h minus f of x over h, right? So, well, a plus h, right? So now the trick is, they did this little variable change on you to try to confuse you, I guess. What if you replace the h with x, right? So instead of writing this, you write this. It's the same thing, it won't even matter, right? It's just a dummy variable, you can change it if you want, right? So that's what's going on. The x here is sort of like the h that you remember from your original form, right? And here they happen to plug in a equals 1, right? So if you consider your function to be ln x, so if we set f of x equals ln x, then it means I can find the derivative evaluated at 1 to be equal to the limit, let's use this guy here, as x goes to 0 of ln of 1 plus x minus ln of 1 all over x, right? Ln of 1 plus x, can't really do anything with that. What's ln of 1? That's just 0, right? So we don't even worry about it over x. Now you might notice that this guy is the same one they asked us about, right? So the question is, how do we know it's 1? Well, we know what the left side will give us, right? Because we know what the derivative of ln x actually is as a formula. So what is it? It's just 1 over x, and we're evaluating that at x equals 1. And so we're done. Other questions?
I'm curious, how do you use the definition of derivative to find the
Well, the definition helped me to figure out the right side.
if we just replace the a replace the 1 plus x.
Yeah, your a is like 1, right? So instead of a, I just wrote 1 here. I take my f of x to be ln x. And so instead of x, I write 1 plus x, right? Just by plugging in 1 for a.
But I'm not asking about the question, I'm just asking about the definition of the derivative to find the ln x.
The definition of the derivative to find what?
ln x.
Oh, well, this is how you'd find it in general, right? That if you wanted to find the definition,
I know ln x equal, the derivative of ln x equal 1 over x.
yes.
But if we use the definition of the derivative, how to find it?
Oh, you mean, so you're not asking this question, you're actually asking how do you actually do this? Or you're actually asking how to compute that? We could do it, but we don't have the machinery yet. So what we can do is in 5.7, I think, you'll learn how to actually do that, something like that. So we'll actually come back to that. We didn't need that right now. In terms of the definitions we're using, we take them as definitions. To figure them out, it's sort of more sophisticated to figure them out in the first place. But in 5.7, I think it's 5.7. No, it's not 5.7. 5.8. We're gonna learn some new techniques to do with limits, and then we can come back to that. So you can remind me.
49.
So to do that directly is sort of a little tough. It's not impossible. 49. We're still in 5.2? Why not? What's 49?
1 to 14, and then 51 to 69.
Okay. What else?
43. 43.
What's 43?
Find the formula for f of n, if f of x equals ln x minus
So f of x equals ln x minus.
No, LCN of x.
ln of the entire thing.
Trying to determine
ln of the entire x minus 1.
So
You want to find the formula for the nth derivative.
find the nth derivative at x.
Yeah.
Okay. Yeah. So I just find this a bunch of times and try to see a pattern. So what is the first derivative? It's just 1 over x minus 1. And if you find the second derivative, what do you get? Which this I can write as x minus 1 to the minus 1.
Negative 1 over x minus 1.
Out of x minus 1 to the minus 2. Find the third derivative. x minus 1 to the minus 3. Fourth derivative. Minus, I'd write it like this, 2 times 3 times x to the minus 1 to the minus 4. Do we sort of see the pattern? So notice that, for one, the amount of derivatives you take is equal to the power over here, right? So I have 2 derivatives, that's the power right here. I have 3 derivatives, that's the power right here. I have 4 derivatives, that's the power right here. So I already can see one part of the formula. I can see that f to the n of x would be equal to x minus 1 to the minus nth power, right? What about the coefficient though? Notice for the first derivative we're positive, then negative, then positive, then negative, then positive. It's actually going to alternate sign. Anyone know how to get an alternating sign?
Negative 1 to the n minus 1. Negative 1 to the n minus 1.
1 to n.
Right. Minus 1 to the n.
Yeah.
But we're going to need something more, right? Because this means when n equals 1, I get a negative. Whereas I don't want to get a negative when n equals 1, right? So it's just like a plus 1 or something like that. And that's fine. Yeah, now what about the coefficient, the constant? I went from a 1 to 2 times 3. There's going to be 2 times 3 times 4. And 2 times 3 times 4 times 5.
And then it's 1 factorial.
N minus 1 factorial. Does anyone know what the factorial is?
Yeah.
Right. So basically, so that would be the answer. Right? You just dissect it one at a time by trying to match up the derivative with the numbers that you find here. By the way, for those of you who don't know, n factorial is just the product of all integers up to n. Right, so for example, if I write 3 factorial, it's just 1 times 2 times 3, which in this case is 6. Or if I write 5 factorial, it's just 1 times 2 times 3 times 4. That's just shorthand for multiplying all integers up from 1 up to that number. In calculus 3, you'll do a lot more with factorials, but in calc 2, we don't see them very often, so you don't have to worry about it for now. Other questions? Yes.
65.
Am I doing the whole homework or what?
Yeah.
What is?
G of x is.
Huh? G is the inverse of what?
Function of f of x equals 2x plus ln x. Find g prime to
G of x.
G is f inverse,
Of x.
and f of x is what?
2x plus ln x.
2x plus ln x.
Find g prime to.
Find g prime at 2. Okay, so what are they actually asking us to find here?
Derivative of f inverse.
It's the derivative of the inverse function. This is just saying f inverse derivative at 2, which we actually know how to do that. That's just 1 over f prime of f inverse at 2. Or if you want to write it using this notation, it's f prime of g of 2. Right? So now all we have to do is figure out what is f prime, what is g of 2, and you plug them in. Right? So f prime we know. It's just 2 plus 1 over x. How do I figure out g of 2?
Set up 2 equals to 2x.
So g of 2, this is just the inverse. So I need 2 is equal to 2x plus ln x, which means my x is equal to 1. Right? Plug in 1 into ln, that goes to 0. Then I have 2 times 1 gives me 2. So x equals 1. This means g of 2 equals 1. And so this means g prime of 2 is just 1 over f prime at 1. And so I just plug in 1 here, and that's 3. Questions on 5.3? Yeah. Because as you guys know, this is the only time we're meeting this week, right? So Thursday is a Monday schedule. So City College decided that Thursday is a Monday. And so we won't have class on Thursday, and next week there are no classes at all Monday and Tuesday. So I'm not seeing you again until like next Thursday. So we need to get a move on. Okay. Questions here? 3B. What is the question? ln of ln of e to the 10. This. And what are we supposed to do? Just simplify it?
Yeah.
Okay.
So the ln of e cancels out.
Alright, so inside here, these are inverse functions, so that just cancels out. And we just have e to the 10.
And that cancels out.
And then this cancels out, so we have 10. Right, so that was 10.
67. The integral from 1 to 2, e to the 1/2 over x squared dx. E to the 1 over x. Sorry.
Ah. Didn't I ask that on the quiz?
Yeah.
Yeah, but I made it the indefinite integral. So let's see who got it on the quiz. Like what was the trick here?
E to the 1 over x with the u. I mean, u 1 over x with the u.
Yeah, you can say u equals 1 over x, so your du is going to be minus 1 over x squared.
So you bring the minus out.
So the minus you can factor out. Minus du is just 1 over x squared dx, right, which is this guy here.
E to the u du.
So I just have minus the integral of e to the u du.
Minus e to
And I know x goes from 1 up to 2. I saw someone in the tutoring center today plugging in the 2 into the u. Remember, the 2 goes with the x, right? Keep a note of that. You can't plug those numbers into the u's. Okay, so we know how to integrate e to the u. What is that? It's just e to the u. Between x goes from 1 up to 2, which means if I'm plugging in these numbers, I have to plug them into x, not u, which means I have to put this back. So it's minus e to the minus 1 over x, which that was the answer for the quiz. Right, that's what you should have gotten. So now we plug in the 2, right? And plus when you plug in the 1.
Isn't
Oh,
it
is that
positive?
the exponent?
Isn't it just positive because you use 1 over x?
Oh, this. Yes, it was just 1 over x. So it's just minus radical e plus e. I mean, there's not really crazy. Don't have to simplify that. That's fine. Other questions?
21.
21.
So limit of x approaching 3 of e to the negative 2x cosine x.
Okay. What do you guys think that's going to be? First of all, you can write this guy like that, right? Now, what is the worst case scenario for the top? Right? It's going to fluctuate. Ultimately, it's going to go between plus or minus 1, right? Keep bouncing up and down as soon as that's happening. What about e to the 2x? It goes to infinity. right? So this guy, the numerator is just it's going to be very small numbers bouncing between -1 and 1. The denominator, though, expands without bounds. So you sort of have like a constant over infinity. What do you get? 0. So you use a little bit of intuition there. Strictly speaking, you have to prove that a lot more rigorously, but that's good enough reasoning. Other questions? By the way, 5.8, we're going to come back with limits, and we're going to be able to do a lot of crazy limits with what we're going to be learning. Other questions?
Yeah.
I don't necessarily remember what the question was about, but I had trouble with the domain, and the thing was f of x equals to radical 3 minus e to the 2x.
Okay.
And then I think I had to find the inverse of that effect.
Was that we have to find the inverse?
Domain of the inverse.
Domain of both.
That was A and B. There was A and B.
Okay, so what was A asked us?
Find domain.
Domain of F?
Yeah.
And domain of F inverse. Okay, so what's the domain of F? What do you have to do for a square root to work?
Says to be greater than
Right, you need 3 minus e to the 2x to be greater than or equal to 0, which means you need 3 to be greater than or equal to e to the 2x, which means ln of 3 must be greater than or equal to 2x, which means so x must be less than or equal to ln of 3 over 2, right? So that was your domain. So you can, many ways you can write this. You can use interval notation. So from minus infinity up to ln 3 over 2, for example, if you want interval notation. So x must be in that for your domain. So everything on the real line from negative infinity all the way up to ln of 3 over 2 is in your domain, right? Okay, how are you going to find the domain of the inverse function? So you guys actually found the inverse and then did it?
Yeah.
You could also do it by finding the range of the original function, right? Because domain and range switches. So if you can figure out what happens to the y values, you'd figure out what happens to everyone else. So I'd probably have looked at that. So basically, so which way do you guys want to do? Do you want to find the inverse function? I'd probably look at the range if it were myself, but let's, okay, so here we have y is equal to the radical 3 minus e to the 2x. For f inverse, you switch x and y. Solve for y. So x is equal to the radical of 3 minus e to the 2y. This means x squared equal to 3 minus e to the 2y. This means x squared minus 3 equal to minus e to the 2y. Or I can just move the minus over here. So it's 3 minus x squared equal to that. I can log both sides to give us 2y. So y would be equal to ln of 3 minus x squared all over 2. And so the domain of f inverse would be the domain of this function. What do I need for this function to work?
minus x squared.
3 minus x squared must be strictly greater than 0. How do I solve that?
X less s minus 0.
X squared less than 3?
Not at all.
Doesn't work. It'll be a finite range, finite length interval. Because y equals 3 minus x squared looks like what? It's like that, right? It's only positive between one point and another point. Where are those points?
Radical 3.
Minus radical 3 and radical 3, right? Another way you can look at it is you could have factored this 3 minus x times radical 3 plus x. And then you'd still get these two that way. But then you have to test the intervals, right? So you solve for x, you have a minus radical 3 and a positive radical 3. And what you do is you plug in numbers. So you can plug in something over here, like minus 2. If I plug in minus 2 here, I get 3 minus 4, which is negative, so it obviously doesn't work. You can plug in a number in between here, like 0. I have 3 minus 0, which is obviously greater than 0. So the middle works. Plug in a random number over here, like 2. Again, it won't work. So you'll realize that the domain of f inverse is only from minus radical 3 to radical 3, non-inclusive.
But in the back of the book, the answer said from 0 to radical 3.
From 0 to radical 3. Oh, it has to be positive because when we square, yeah, I didn't check. When we squared, we didn't take into account that this wasn't a plus or a minus. So when you get here, you have to remember, this is not the original function. We actually solved for it from this function. So the left side we actually don't care about. We don't care about the positive values because of the original is defined to be positive. No, it's not an absolute value thing. It's just because the original guy we were solving for didn't work on the negative side. So this guy won't either. Let's try to complete 5.4. Yes?
How you use the range? How you use the range?
For the same thing, so f of x equals 3 minus e to the 2x. Was that it? Okay. So what did we say the domain was? ln 3 over 2. Right, so when your x is ln 3 over 2, what do you get? So if x is ln 3 over 2, then you'd have 3 minus e to the 2 ln 3 over 2. Right, what would that give you? Right, so the 2's would cancel here. E to the ln of 3 is just 3, so that would actually give you 0. So you know that 0 is going to be the lowest. And you can notice as you get less than that, right? Now when x starts to get less than that and go negative, right? Eventually it will keep going this way and go negative. You're having e to the negative of something, which means you're getting smaller. This guy is going to approach 0 as your x gets smaller, which means ultimately it's going to tend to radical 3, right? Because this guy's going to 0. So you know you're going to start at 0, but as your x goes this way, this guy is going to 0, so you end up with a radical 3. So from that you can say, oh, it's going from 0 to radical 3. to me was a lot easier than going through all that. And then forgetting that you didn't have to worry about the negative sign. I don't know why you guys like doing everything the hard way. Let's continue with 5.4. We actually don't have a lot here really. I actually wanted to try and finish 5.5 today, but I don't think that's going to work anymore. Because yeah, we have like a whole week before we see each other. More than a week. Okay, let's see. Let's go back to graphs. I skipped this last time because I wanted to get to those crazy integrals, because they were fun. But I skipped over some graphs, so let's go back to graphs because they're very useful with things like computing limits and things like that. Knowing the graphs is actually a great benefit. So for example, we looked at the graph of say a to the x, where a is greater than 1. And what did we say that looked like? It's like this guy, right? Passing through 1 here. Right, so this is y equals a to the x for a greater than 1. Now notice that we have transformations, so you should remember those guys. So what if I ask you about y equals a to the minus x? Reflect where?
X.
It reflects in the y-axis, right? So you have to remember that when you change your x negative, it's a reflection in the y-axis. Right? So this guy would be that graph, right? It's also equivalent to a to the x if a is less than 1. Right? Do we see y? So if your a is that kind of number, right, that means you can write a to be equal to 1 over something where c is greater than 1, correct? So that would mean a to the x would be equal to 1 over c to the x, which is equal to c to the minus x. Right? So this is actually equivalent to that kind of guy. Right? So if your a is greater than 1, it's actually pretty much the same as just making if your a is less than 1, it's pretty much the same as making the exponent negative. You'll still get this graph. What about y equals minus a to the x? Reflecting that, right? All your y values become negative, so now you're going to look like that. Right? This is y equals minus a to the x. What about y equals minus a to the minus x? Where you're going to take that guy over there and you're going to flip that, so that's going to go down like this. So these guys, for example, you can tell right away about their limits, right? So like limit as x goes to infinity of this guy is going to be infinity. Limit as x goes to negative infinity is going to be 0. Whereas with this guy, limit as x goes to infinity is going to be 0. Limit as x goes to negative infinity is going to be infinity, right? So just by looking at the pictures, you can have a lot of information that can really help your intuition when dealing with limits. Same thing with this guy. You can know if x is going to plus or minus infinity, you can see exactly what's going to happen, right? You can sort of see it in your head. It's really good to have that intuition from the graphs. So I thought I'd just remind you about how these graphs work. We're going to come back to this in 5.8. Like I said, we're going to do limits again. This is going to be easy compared to what we were doing, but let's do it anyway. Limit as x goes to infinity of y and limit as x goes to minus infinity, where a, y is equal to 5 to the x, b, y is equal to 1/3 to the x. That's not me. Okay, this should be quick. Y equals 5 to the x. What does that look like? Right, just looks like that, going through 1. How can you identify whether or not it's 5 to the x? You can do something like plot a point, right? So if this is 1, that would be 5. So you can put 1 comma 5 on this to sort of show it's 5 to the x. Limit as x goes to infinity of 5 to the x. Infinity. Limit as x goes to minus infinity of 5 to the x. 0. Limit as x goes to minus 2 of 5 to the x. One over 25, right? You can literally just plug it in, 5 to the minus 2. Right? Don't forget that about your limits, right? If your function is defined, you can just literally just plug in the number. So, y equals 1/3 to the x. What does that look like?
Absolute steep version of
It won't look like that, no.
Is that flipped over the y-axis?
It'll flip like this. Why?
Because it's 3 to the negative x.
Right, this is 3 to the minus x. It's the same thing, right? By the laws of exponents. So that's what your graph's going to look like. You can plot a point if you'd like. Say minus 1 will actually hit the point 3, right? So minus 1 comma 3 will be on this graph. Negative infinity of 1/3 to the x. This guy, as I go to infinity, I get 0. As I go to negative infinity, I get infinity. Right? By the way, that problem you guys asked me about earlier, about the e to the minus x times cosine, it's the same sort of thing. That's how I know this guy went to 0, because I know how minus x behaves. I could just see the picture in my head. Oh, that's just decreasing. And the cosine is not going to do much damage, because it just bounces up and down between minus 1, plus or minus 1. This guy's heading to 0, so it ends up to like 0 times plus or minus 1. So I know overall it would have been 0. So a lot of times you can know this without doing any calculations, and a lot of times you have to do that, because we're going to do other things like improper integrals, which we'll get to, where you're taking limits while doing something else. So the quicker you can get that limit out of the way without too much calculation, the better, right? So the graphs actually help you a lot with that intuition, and so knowing the graphs is pretty important. So I just want to make sure I mention them. And again, the larger the base, the more steeper it gets, right? So if I compare, say, 5 to the x to something like 6 to the x, 6 to the x is going to be steeper on this side, but it'll actually be lower on this side. I hate using colored chalk. want to emphasize. Because it's hard to erase colored chalk. Right? So not only do larger bases increase faster, but they also decrease faster. Right? So they'll get smaller on this side, but bigger on that side. That's also something to consider if you ever have to compare two of these guys. You should know that as you're going to negative infinity, this guy's bigger, but as you're going to positive infinity, this guy's bigger. Things like that also help your intuition a lot. Because we'll often have to do limits where there are different kinds of functions mixing together. So knowing how each behaves will help you a lot. Okay. Now, something else I wanted to show you, alternative to log differentiation. I promised I'd show you an alternative. And it uses the following rule, which we covered last time. A to the x, if I want to write that as base e, how does that look? E to the ln of a to the x. Or in general, this is something we can do in general, by the way. It's not necessarily something that I need an exponential to work with. In general, if I know that my function is positive, because I need to make sure it works in the log, then f of x I can write as e to the ln of f of x, right? By the same rule. Yeah, seems legit. Okay. So here's what I propose. And we know how to differentiate functions like that, right? Also recall, something I also asked you on the quiz, the derivative of e to some function is
e to the u dx.
u prime times e to the u, right? Just take the derivative of the power times the original function. Okay. Putting all these together, we can actually get around log differentiation. So let's do something that we did by log differentiation before. Let's say I wanted to differentiate x to the x. So remember, before what we did, we said y equals x to the x, you log both sides, you do the derivative on this side, you multiply by y, blah, blah, blah. You did all that, and you sort of solve for it. You had to do implicit differentiation. But it turns out, I could have just done something like this. This is just the derivative of e to the ln of x to the x. Right? And that's just the derivative of e to the x, ln x. And what's that? Well, it's going to be the derivative of the power times the original function. So the derivative of the power, we need the product rule for, right? So you differentiate x, leave this, so it's 1 times ln x, plus you differentiate ln x, leave the x, so that's x over x, which is 1. Don't really want to skip the step though in case someone misses it. And then this is, you rewrite the original function. So now this guy is going to be ln x plus 1 times the original function, which is just x to the x. And which is what we got last time. So I did it without having to log both sides and then implicit differentiation and moving things over. Right? When is this useful is in that case when I tried to trick you guys, well, I did trick you guys, and I put two functions side by side, and one of them you had to do log differentiation, the other you didn't have to do log differentiation. So the thing is, if you know this, you never have to split things up and do the problem in two parts. You just change one of the functions. So we had something like y equals x squared plus sine x to the x, right? And what we had to do is, you take this to one side, you deal with him with log differentiation, and then you come back and plug him in. But the thing is, I could have just done this. Right? just rewrite them right there. Keep everything together. And now I can find y prime. So that's going to be 2x plus, I'm going to take the derivative of the power, which is product rule. Derivative of x is 1 times this, ln of sine x, plus leave x, differentiate ln of sine x, which is 1 over sine x, times the derivative of sine x, which is cosine x, times the original function. So this means y prime is just 2x plus ln of sine x plus x cotangent x times the original function, which you'll see is the answer we got last time. Difference now is I didn't have to break things in two parts, right? Everything was very contained, very controlled, very relaxed, right? But the trick was just to rewrite this guy in terms of base e. And the thing is, differentiating with e is easy. It's just the derivative of the power times the original function, right? That's why it's called the natural number. It makes calculus easy, sort of, right? You don't have to go and do something all separate over here. Rewrite this in base e, and you're done. After going through the rules, of course. So, thought I'd show you guys that. What else do I want to show? How to find the derivative of the general log function. Did we do that? Find the derivative of log to the base a of x?
It was at 8.
Let's do the general log function. That's really the main last thing in this section. So let's say I want to differentiate log to the base a of x. Right? What is that? Right. So by the change of base formula, I can rewrite this guy in a convenient base. What's the convenient base for calculus? E, right? So I can rewrite this guy as ln x over ln a, right? Now remember, ln a is just a constant. And so how do I differentiate that? We differentiate ln x, which is just 1 over x, and the constant just stays. So you end up with 1 over x ln a. Right? And that's actually the rule. To differentiate a general log function, which from now on you should know, right? It's just 1 over x times ln of the original base. Let's generalize this by the chain rule. What is the derivative of log to the base a of u? Right? Where you may or may not think u is a function of x. What do you think the answer is going to be? 1 over
u ln a over du dx.
u ln a, right? Derivative of the outside function multiplied by the derivative of this function. So I just make it u prime over u ln a. So that's the generalized version. probably better to memorize this than that. Because if this is just an x, then x prime is just 1, and you end up with that formula over there. Okay. Let's do a couple examples. Example. Find the derivative of log to the base 2 of x. Example. Find the derivative of log to the base 5 of radical x times x plus 1. That's probably going to take up more space over here. Find the derivative log to the base 3 of 10 plus 7 cosine x.
No. Yay.
Okay.
It's 5.4 homework.
Yeah, figure that out on yourself. That was the last thing I was going to do anyway. Homework due next time. I'll probably give a quiz. Pass up the homeworks that you have now. So next Thursday, 5.4 homework due. We have a quiz on 5.4. All right, get out of here. Be safe. See you guys Thursday. Fire drill.